Hey, can you go down to the pad? I wanted to the first was I thought I'd just sort of make a general announcement about quiz. I guess the first thing to announce is I don't know that we even put this in our materials, but I guess we're gonna drop the lowest grade in the quizzes. We're gonna do that. So you're welcome to get a 2 or a 0 or something. You could do it just for the thrill if you wanted, because we're gonna drop it. The second one is that if you know ahead of time that you're gonna need to be away on a Friday, contact either me or better the TAs. Just contact me or the TAs ahead of time. We'll be happy to make alternate arrangements. We do it every week for several people. So if you have a good reason, bad reasons include I couldn't possibly be awake by, what time is that? 9:40. This is not, but most other reasons are going to fly. However, no reason, we actually can't give them after the class. So once the quiz is given, that's it. So approaching us later in that day, saying I wasn't able to wake up in time or something like that, isn't going to fly. And the reason is that we actually post them immediately after the class for the SITN students and things like that. So that's how that works. So again, problems with quizzes and scheduling, contact us ahead of time. No problem at all. Contact us after. Don't even bother to contact us afterwards, because it just isn't going to work. I mean, unless there's some really, really good reason why you couldn't take the quiz but didn't know it ahead of time. I guess the other thing I wanted to mention was, yes, believe it or not, the midterm is actually next Friday. So I guess that's early in the midterm cycle, and I mean among those classes that have one midterm. If you have 2 midterms, I think you're already into your midterm cycle already in some classes. That's next Friday, and just to this is just sort of as a heads up. I think 50-minute midterms are just idiotic. I don't understand how anybody can do anything in 50 minutes. So what we're going to do is it's going to start at 8:30 next Friday, and it'll go till 9:50. So that's a reasonable amount of time. That's the idea. So, but please make a note of this. I'll probably announce it one or 2 more times. Somebody is going to march in the door at 9 o'clock, I'm sure. Don't let it be you. So, okay. Then the other thing is I've had a couple of inquiries about what the format should be, and really it's up to you. So here, let me discuss the alternatives, and you can think about it or whatever, and then get some feedback to me. Here are the alternatives, and I'll tell you which ones. Well, I'll make it clear which I like and don't like. Okay. One is just totally closed book or something like this. I think this is silly, because you'd have to just things you'd have to memorize and things like that. So I would even, unless I doubt any of you want that anyway, so that's simple. Now an alternative, which is close to that, is something like this, that you bring in like a Laplace transform table, right, and maybe a page or 2 of your own notes. That's alternative 2. That's my favorite, to tell you the truth. And then the third is you can bring anything you like. Well, I don't know. Let me just get a sense right now. It has implications, of course, as to what we put on the midterm, right? Right. So, I don't know. Any thoughts?
Door number 2.
Door number 2?
Yeah.
All right. Good. Okay. So for those of you who just can't possibly wake up at 9 and are going to watch this on tape later, this is the cost of watching the class later in the day at Terman or wherever, is you don't get your voice counted. It was door number 2. That means that you can bring a Laplace transform table and maybe a single sheet 2-sided with anything you want to put on it, any notes you like. Yeah. 8 by 11. Yeah. Do I have to specify a font size? Font size, yeah. Well, yeah. Font size exceeding 6. There. Right. It could be 8 by 11 in microfiche or something. Okay. So that's good. Let's consider that set, unless I hear some torrent of comment going against that decision. That's what it is. Okay. Let's just jump right back into our material, which is partial fraction expansion, which of course we don't care about at all, except that it gives us a way to carry out inverse Laplace transform. I mean, that's really the only important part about it as far as we're concerned. It comes up in other fields, but this is the important one for us. Up till now, we have assumed that the poles are isolated. In other words, they're distinct. So all the poles are different. And remember what happens in that case. When all the poles are different, the basic result, I got to find it now, is that you can factor, is that you can write a rational function as, let's see, well, here it is. We can write it in this form, which is the partial fraction expansion. Now, in fact, this form is not valid. It will fail if this denominator polynomial here has any multiple roots. In other words, if this thing has any repeated poles, you cannot put f in this form. First of all, this will be pretty obvious if you just try it. In terms of all of our methods, they'll just simply fail. For example, if you try to form these linear equations and solve linear equations, the linear equations you write down will be inconsistent. You just can't do it. So the question is, what do you do in that case? Well, let's see what happens. It's going to be a little uglier. Well, in fact, it's going to be substantially uglier. Fortunately for us, it turns out, well, I mean, the nicest thing would be if, in fact, repeated poles never occur in practice. That would be very nice. And I'm very, very sorry to report to you, it's not the case. They do, in many important cases, you have repeated poles. Now, the good news is that the multiplicity is only 1 or 2 or is only 2 or 3 or something like that. And rarely is it more than 3. On the other hand, the general formulas are going to be very unattractive. So anyway, all right, so here it is. F has this form, and the question is, what's a generalization of partial fraction expansion that works in this case? And the answer is this. It's not pretty, but I'll show you what it is. Basically, what happens now is for every pole, of which there are L distinct poles, you will have some terms in a partial fraction expansion. They look like this. This is the familiar term in a partial fraction expansion. The other terms look the same, except that the power of s minus lambda is increased. So here it's to the 1 power, then squared, cubed, and so on. Each of these has its own residue now. So now the problem is that, in fact, you end up with exactly the same terms, n terms. There are precisely n terms here. And in fact, it makes perfect sense. You have k1 poles at the complex number lambda 1. Well, you've got k1 terms in the partial fraction expansion associated with the pole lambda 1. What they are is they're something over s minus lambda 1, something over s minus lambda 1 squared, something over s minus lambda 1 cubed, and so on. And you have as many of these as you have the multiplicity of the pole here. So again, it's not pretty, but examples will make it very clear what it means. And the other nice part is that this is a lot uglier than any case you will ever actually encounter. Okay? That's the general form. So let's see how this works. Here's an example. And this is, by the way, the type of example that you'll see. So this is actually an example you will see. It's 1 over s squared, s plus 1. Okay? So here there are a total of 3 poles, right, counting multiplicities. There's 1 pole at s equals minus 1, and there are 2 poles at s equals 0. That's what this says. Okay? So it's very easy to write down the form of the partial fraction expansion, which is always the first thing to do. What you do, the poles which have multiplicity 1 are simple. They correspond just to the same old terms we've looked at before. So you get an r3 over s plus 1. Now here you have an s squared. That's a multiple pole, multiplicity 2. So you have these 2 terms, r2 over s. That's the familiar term. And here's the new term, r1 over s squared. So that's the form. And in fact, the truth is, once you've got the form down, you're done. I mean, there's lots of sneaky ways to find r1, r2, and r3, just as before. And we'll look at some of them. But in fact, in general, we won't look at them. I mean, if worse comes to worse, if you get into a really desperate situation here, you can simply clear denominators and start equating coefficients. And the answer will pop out. So the really important part is understanding what the form of the inverse Laplace transform, sorry, the partial fraction expansion is. Okay. Now, if you put it in this form, it turns out the inverse Laplace transform in this form is also easy to get. When you take the inverse Laplace transform of one of these things to a higher power, what you get are terms of the form e to the lambda t, right? But with these powers of t in front. Okay? Now, that's very interesting. You've already seen this once. You've seen it for second-order systems. For second-order systems, the denominator has degree 2. It's a quadratic. And there was one, if you remember, there's a special case. I guess it's called critical damping or something like that. And it basically says that both poles of the Laplace transform are equal. Well, that's the repeated root case. And sure enough, what came up there was a t e to the lambda t term. So, in fact, this is general. So what this says is that basically from now on, right, for the rest of your life, or as long as you care about any dynamical system, electrical, mechanical, electromechanical, or anything, any otherwise, you, from now on, multiple poles and terms of the form t, e to the lambda t, will be permanently linked. They mean the same thing. If you look at a solution and you see something of the form t e to the t, t e to the minus 10t, t cosine t, this will mean there are multiple poles. If you see multiple poles, you will expect to see things like t e to the lambda t in the time domain. Period. That's the way it works. And actually, this is an important thing to know. So we'll that's generally. Okay. Now, how do you find these r's here? Well, you know, the same types of tricks work. And so let's try this. It turns out here's the really good news. The really good news is that finding the residues for the non-repeated poles is the same as before. So in other words, to find R3 here, the trick I do here is I multiply both sides by s plus 1. Then I evaluate the result at s equals minus 1. I can almost do this with my finger doing this. And so in this example, you just get 1. I won't even go through the details. Okay? Now, once you've found those, it remains to find R1 and R2. And you can do all sorts of things there. You can actually work out, you can clear the denominators and solve for two equations and 2 unknowns. This is pretty much on the boundary for me. I don't know, I think it should be for you as well. In other words, that the number of linear equations you should attempt to solve by hand. For me, it's 2. 2's a good number, because anyone should be able to solve 2 linear equations and 2 unknowns. That's a reasonable thing to attempt. Already for 3 and 3, it depends on your level of desperation. It also depends. If it's a very simple set with lots of zeros in the coefficients, you know, go ahead. I'll attempt it. But so here, I mean, you could just do this. If you do that, you'll end up with this. And of course, in the end, when you end up with a partial fraction expansion, you should check it. And so you just clear the denominators and make sure this is equal to what we started with. Now, it turns out that there's lots of other methods, and I'll just show you a couple, and then I'm not going to spend a lot of time on it because, I don't know, actually just doing it is more instructive, actually just getting a problem, trying 1 or 2 methods. You can do something else pretty clever. For example, let's go back to this one. Here, let's go right back. In fact, let me just repeat it right here, and we'll just do it right now. So you have 1 over s squared times s plus 1 equals r1 over s squared plus r2 over s plus r3 over s plus 1. Let's try using this trick of multiplying by something and then evaluating. So let's try a few things. Let's try to get r2, for example. What should I do if I wanted to get r2? Let's multiply both sides by s. Can everyone do that in their head? Okay. Now, let's plug in s equals 0 and see what happens. Well, over here, I get s r3 over s plus 1. I plug in s equals 0, and I get what? Okay, that's excellent. That's what we wanted. We wanted r3 to go away. When I multiply by s and evaluate s equals 0, what happens here? That's just what we wanted. Okay, now the bad news. Multiply by s here, and what do you get? R1 over s. Now I plug in s equals 0, and I'm in some deep trouble. I'm also in deep trouble here. So this method failed completely. Oh well. Let's try to get R1. Can we do that? What would you multiply by? Okay, and if you multiply this thing in your head, everyone please do that by s squared. Got it? Or I'll do it for you. Here. There. Now what happens when I plug in s equals 0? What happens? Well, everything's going to work. I get R1, and over here I get 1. That was pretty easy. So what this says is finding the highest or the residue associated with the largest degree term is actually just as easy as it was before. Since in practice the largest multiplicity of a pole you will ever see is 2, and occasionally 3 under some bizarre circumstances, right? This is really not that bad. Now, if you knew R1, and now we got R1 and R3 painlessly, and R2 remains. Actually, at that point, it's not that hard, right? Because you could just, for example, you could just write out all the equations. You combine it with your check, and then R1 will just pop out right in your face. That's what it's going to be. Okay, so I think probably that's enough to say about that. There are lots of other formulas. They are unattractive, and I don't remember these things. Well, this one I do. Here. I don't remember this, or I remember that there exists a formula, something like that, but I don't remember it. So in practice, it turns out that usually the multiplicities are small. They're either 1 or 2, and very occasionally 3. And so there's no point really knowing general formulas like that. It doesn't really matter. I mean, you can write it down somewhere. It's more important to know there are such things, and this is how it's done. Okay. Okay, finally, let's look at non-proper rational functions. What we're doing now is we're looking at each of the assumptions about partial fraction expansion. The basic assumption, I mean, when it's easiest is when it is a numerator divided by a denominator. The denominator has all distinct roots. In other words, so the poles are all different. And the numerator has a degree less than the denominator. I don't know if people remember that, but that was a requirement. Okay? Now we just dealt with the case of what happens if the denominator has multiple roots. Now we know what to do there. What happens if the numerator has a degree higher than or equal to the denominator? And that's what we're going to look at now. So if I have a rational function and the degree of the numerator is less than the degree of the denominator, we'll call that strictly proper. Okay? It's proper if m is equal to or less than n, and it's non-proper if the order of s in the denominator is higher than the numerator is higher than the denominator. So here's what these affect. What they affect is the value of s when s is really large. If s is really large, what's the value of this approximately if s is really big? What is it? Yeah, so basically, if s is large, then you have f of s is about equal to b sub m over a sub n, s to the m minus n. Everybody agree with that? And the reason is that when s is really large, then s squared is a lot bigger than s, and s cubed is a lot bigger than s squared, and so on and so forth. And in particular, s to the m is way bigger than all the other terms here. And s to the n is way bigger than all the other terms. Now, it doesn't matter if, for example, a sub n is small. Because if I make s big enough, the fact that it's a higher power is I'm going to make up for the fact that maybe an is small compared to a1, which might be big. Eventually, for s big enough, these two terms are the only these terms will dominate. So for large s here, this f is approximately given by b sub m over an divided by to s to the m minus n. Now, if this is strictly proper, this is negative, and it says that f is small for large s, right? And if it's non-proper, it says it's big, it's getting bigger. Or strictly, if it's right non-proper, right? It says that this is actually a power of s. So that's the idea. Okay. So the partial fraction expansion requires a strictly proper f, and if you don't have that, you can always just divide it out. You just do polynomial division. You divide the denominator into the numerator, and here's what you get. A polynomial, which is, I guess, the quotient or something like that, and then d is the remainder. I guess that's what they call it, right? Divided by a. And d over a, the remainder will have a degree less than the denominator. So this, you can now apply partial fraction expansion to d over a. Moreover, this is just a polynomial in S, and taking the inverse Laplace transform of a polynomial is easy, because the inverse Laplace transform of 1 is delta, of S is delta prime, S squared is delta prime prime, and so on. So what this says in the end is that you now know how to take the inverse Laplace transform of any rational function. Okay? If the degree of the denominator is more than the degree of the numerator, it says you're going to have some delta terms there, maybe delta, delta prime. And in fact, the highest power, or the highest derivative of delta you see, corresponds precisely to what some people call the pole zero excess, which is n minus m. Okay, so this is what you see. So here's an example. Here's a rational function, 5s plus 3 over s plus 1. We can't write out the partial fraction expansion of this immediately. First thing you must do is divide s plus 1 into it. And you get 5 minus, and then the remainder is 2. So now taking the inverse Laplace transform is easy. 2 is just 5 is just 5 delta of t. This term is, of course, minus 2 e to the minus t. And so there it is. So the inverse Laplace transform of this is that. Now, this should actually be burned into your head now, that, in fact, part of what needs to happen is these types of relations between this and this. You have to actually develop not just a facility for going back and forth mechanically, but in fact the intuition and feeling for this. So you should expect this when you see that, and vice versa. Almost immediately, almost like speaking a second language or something like that. The translation should be automatic. You should get the feeling for it and stuff like that. Here, when you see this, you should instantly say, hey, you know, the degree of the numerator is actually not less than it's just equal to the degree of the denominator. A little light should come, and then some neurons should fire in your brain and say, oh, say, that means this thing isn't strictly proper. This thing by itself doesn't have an inverse Laplace transform. A partial fraction expansion. I first have to divide it out. You should know that says, oh, the light bulb should go off and some more neurons, and it should say, hey, probably that's because this thing is going to have some delta impulses at the origin. That's what's going to happen. And then if you're really sophisticated, you could say, actually, it's going to have an impulse at the origin, number one, and not even a delta, but not even a delta prime. Okay? If I do this, right, if I multiply this by, or if I made it 5s squared plus 3, there's a modification. We don't know what it is. This is wrong now. This is totally wrong. Okay? When I write that out, what is the inverse Laplace transform going to have in it? What's it going to have at the origin? I have no idea what the inverse Laplace transform of this expression is. It's a rational function. 5s squared plus 3 over s plus 1. What are the terms qualitatively in it? It's going to have an s squared. It's going to have a delta prime. This is going to have a doublet. This is going to have a doublet, a delta function, a delta prime function, and an e to the minus t term. What are the coefficients? I don't know. I'd have to do the arithmetic and the algebra here, but I don't know what it is. So that's the idea. Okay. Well, this finishes up our treatment of rational functions, partial fraction expansion. But the bottom line here is that you can now find the inverse Laplace transform of any rational function. And actually, fully understanding this relationship is very, very important. In fact, the next lecture is on absolutely nothing. There is, in fact, nothing new. Nothing new here. Absolutely nothing new. It is simply a long discussion of what you now know about inverse Laplace transforms. What does it mean about, we're just going to talk about qualitative properties of signals and things like that. Okay? So, but there's no new results here. None of any kind. You know them all. It's just from the last lecture. It's partial fraction expansion and so on. So let's start with a rational function, f, and suppose it's rational and strictly proper. Okay? Then we can immediately find its transform from the partial fraction expansion. Now the partial fraction expansion is a sum of terms. Okay? In front of, there'll be a residue divided by s minus lambda, possibly to the power if you've got multiple poles. That's partial fraction expansion. Now to take the inverse inverse Laplace transform of capital F, we take the inverse Laplace transform of the partial fraction expansion term by term. Each of those is going to have, the residue just pops right out, and we're forced to take the inverse Laplace transform of terms of this form, or if this thing has multiple poles of terms like this. Now what we want to concentrate on here, well actually some observations. The first are that the poles of F determine the types of terms that appear. That's very interesting, right? It says that if you have a rational function and you want to know about the inverse Laplace transform, if your eye should go immediately to the denominator. That's what this is saying. If you want to know what kind of terms appear, are they cosines, sines, exponentials, t times e to the minus lambda t? All of that information is found in the denominator, not in the numerator. The numerator is going to relate to all the residues. Okay? It's the numerator that determines the residues, and vice versa. Now the numerator, if you factor it, these are the zeros. So you've already learned something interesting. It's not specific, but it's an interesting idea. It says that when you have a rational function here, the poles determine what kinds of terms you're going to get. Right? Are they exponentials? Are they sinusoids, growing sinusoids, decaying sinusoids? You know, t e to the lambda t, this kind of thing. That's determined by the poles, and only by the poles. The numerator, or the zeros, now, determine the residues. So if I come up to you and say, oh, you know, I was wrong about f. I got the third coefficient in the numerator wrong. What does that do? It doesn't change the types of terms you have in your answer. It changes all the coefficients in front of them, is what it does. Okay? This relation goes two ways, absolutely two ways. If I show you two time domain expressions, and they have the same types of terms, but different coefficients in front of the terms, then the Laplace transforms of these two things have exactly the same poles, and they have different zeros. Okay, so I won't say much more about that. That's the idea. And what we're going to do now is we're actually going to study each of these types of terms, and what do they mean? Well, so this is kind of easy, and the truth is we've already done this in the second order system case. And you'll see in a minute that once you know that, you know everything, basically. And here's the way it works. If you have a real positive pole, right, then that corresponds to a growing exponential term. This is obvious. Not only that, lambda, the actual pole, which, remember, the physical units of a pole is frequency. It's it's inverse seconds. What that says is if you have a real positive pole, it corresponds in your solution to a growing exponential. And in fact, the doubling time is, you know, whatever it is, you know, 0.693. It's 0.7 divided by lambda gives you the doubling time. So, in other words, so when you look at a Laplace, when you look at a rational function from now on, and if someone, for example, gives you the poles, and there's a pole, if I tell you that I have a Laplace transform which is a 6th degree numerator and a 9th degree denominator, and one of the poles is plus 0.1. What does that mean about the inverse Laplace transform? Well, it's got 9 terms, right? 9 poles. It's got 9 terms. I didn't tell you anything else, so we don't know what 8 of the terms are, but we know what one of the terms is, and that one term is e to the 0.1 t. And that term, do we know the coefficient in front, by the way? Do we know the coefficient in front of the 0.1 t? No. What's it determined by? The zeros, or the numerator, exactly. We have no idea. But we know there's a growing term. That term doubles in what time scale? You can just make something up if you want. I mean, it's 0.1. So it gets multiplied by a factor of e in 10. So in fact, the correct number is 7. So there is a term in that Laplace transform whose size doubles every 7 seconds. Okay? So, and again, I got this. The amount of information I'm going on here is very, very small. I have no idea what the numerator is. I don't even know what the only thing I know about the denominator is it has a pole at plus 0.1. Okay? So this is the type of reasoning that's very important to be able to do. Okay, if you have real negative poles, these correspond to decaying exponential terms, and in fact, the frequency there gives you the shrinkage rate. You could calculate, for example, one time constant gives you the time to decay to 37%. right? 5 time constants is approximately the time to decay to 1% or something like that, and so on. So you could do this. If you see a pole at s equals 0, that's a special case. That's a constant term. That means that there's a constant when you take the inverse Laplace transform, there's a constant or an offset. That's what it says. If you have a complex pole pair with positive real part, that's an exponentially growing sinusoid. If you have a complex pole pair with negative real part, that's an exponentially decaying sinusoid. And if you see any pure imaginary pole pairs, those are pure sinusoidal terms. Okay? Now, if you see repeated poles in there, you get the same types of terms but multiplied by t, by powers of t. Okay? And this is it. So what that says is, if I give you the poles of a rational function, you can actually say qualitatively what all the terms, the types of terms are, before you go off and work out all the horrible details of exactly what the residues are and things like that. Okay? So that's the idea. Or vice versa, if you see a solution and it's got things like, well, if a solution, for example, if part of a solution has minus 0.1 t squared cosine 3t plus 5 in it, plus and all sorts of other crap. Okay? And I take the Laplace transform of this. Oops, I don't really need that. And I take the Laplace transform of this. What can I say? And I don't even know what these are. If I take the Laplace, here, let me put another one in, e to the minus 2t. Okay? There we go. If I take the Laplace transform of this big horrible expression, it's a rational function. What can you tell me from what you see here? So the Laplace transform of all this is going to be called f of s. What can you tell me about f of s? It's got repeated poles. How do you know that? T squared. There's your tip-off. Okay. Let's be more specific. Okay. What can you tell me about, can you tell me anything about the poles? How many poles does it have? It's a serious question here. What's the answer? By the way, every now and then, actually quite often, the correct answer to a question, the absolutely correct answer to a question is, I don't know. This is one of those cases. Of course, we have no idea how many poles there are because I haven't said what this or this is. Okay? But if you want to be, I don't know, more, well, we could say something intelligent about the minimum number of poles. We could do that. Could this be a second order system? No, that's totally out of the question. So we'll come back to that. What is this? When you see this term, there should be a quick neural connection, and it should say something about f. What does it say about f? It says f is b of s over a of s. The existence of this term here says something about b or a, and I want to know what it says. What does it say? Exactly. A has s plus 2 in it. Or, to be really, really technical, all we know is a of minus 2 is equal to 0. Right? That's what we know. Is that a vanishes at minus 2, right? Which means you can say a of s, if it were factored, it has an s plus 2 term in it. Or you can say f has a pole at s equals minus 2. Okay. Now, if I change the sign, I say, oh, you know what? I'm sorry, this is wrong. I just realized it's minus sign here. What happens to do we have to revise our conclusion here? Not in the slightest. Okay? What other terms does A have in it? Yeah, you look at cosine, and instantly there are complex poles, period. There are complex poles. Okay? That's the first thing you say. Then you say, all right, what are those complex poles? Let's do this case first, just for fun. Okay? In this case, what is the complex pole? If it looked like that, what would you have here? Well, you say that's pure imaginary term. Sorry, pure sinusoidal term. That corresponds to poles which are purely imaginary. And what can you say about the poles? What are they? They're what? Plus or minus 3j. Okay? How did the 5 work into this calculation? What does 5 affect here? What if 5 were 6? What does it change? Initial conditions, but here that means what? It means residues. It's residues. This 5, that corresponds to B, right? It's a phase angle. 5 corresponds to B. So in other words, the 5 depends on B and vice versa. This 3, that's the critical number there, and it's the frequency of oscillation, and it is precisely the pole position. Now, there's t squared here. What does this mean about this? If it were t cosine t, what does that say? You have 2 repeated poles, but now you have t squared. Okay? So that says that what is the multiplicity of the pole at 3j? It's 3, precisely. Well, it's at least 3. There could be some other term over here, which is t to the 5 cosine 3t. We don't know that. So it's at least 3. Okay? So the minimum, so this term actually corresponds altogether to 6 poles. That's 6 poles right there, right? It's 3 at plus 3j and 3 at minus 3j. That's the idea. Okay? So I probably shouldn't have picked such a complicated example as our first one, but too bad I did. So that's it. Okay. So, all right, this is the idea. Now you can also be very quantitative, and that's this, that if you have a pole, the real part is going to determine this growth rate or shrinkage rate. If the real part is positive, we're talking growth, and if the real part is negative, we're talking decay or shrinkage rate. The imaginary part of a pole is going to mean the oscillation frequency. It goes in here. Okay, that goes right here. So this is, again, a very, very important thing to know. Here is a picture, which is a very, very important picture. There's a few in this class you have to know and you'll use from now on, and here it is. Here's a term that corresponds to a single pair of complex poles. The poles are precisely sigma plus minus j omega. Sigma is the real part of lambda. Omega is the imaginary part. Now what this shows down here is it's an array of a plot of this. This is, I guess, this is omega equals 30, 15, and 0. And the columns are minus 1.5 real part, minus 0.75, 0, 0.75, and 1.5. And it's arranged as you would see these on the complex plane. Okay? So for example, this is e to the minus 1.5t. That's e to the minus 0.75t. They both decay. Obviously, e to the minus 1.5t decays twice as fast. When you have sigma equals 0, this is the pure oscillatory solution, except in the case, of course, when omega is 0, then it's a constant. Okay? So from any of these, you should be able to go back and forth. In other words, from now on, if somebody tells you there's a pole at sigma plus j omega, immediately you should know what it means. You should be able to sketch that term, and you should be able to go backwards. Someone should say, I don't know, I'm kind of observing this in the solution. What does that mean about a pole? And you should be able to actually go back to the pole location in the complex plane. So qualitatively here, this is an extremely important picture here. So I've drawn the poles, which are these x's. That's, remember how we do a pole 0 plot. And so you draw this thing here, and this is extremely important. Probably the most important figure in the entire course is this one here. And what it says is if you plot poles in the complex plane, they tell you about the qualitative behavior of the associated terms in the inverse Laplace transform. So for example, if a pole is right here, that corresponds to a constant. It's a pole at s equals 0. It's a constant term. If you move along here, that's a decaying exponential. That's a growing exponential. But more generally, your x-axis here, which is your real part, this is negative real part, positive real part. Your real part determines whether you grow or shrink, and moreover, it determines the rate at which you grow or shrink. If you're right on the boundary between growing and shrinking, it says you're constant. If you're slightly in the, what people call the right half plane, if you're slightly in the right half plane, it means that term grows slowly. If you're slightly in the left half plane, it means that term shrinks slowly. If you're way, way, way over here, these are terms that decay very rapidly. These are terms that grow explosively. Okay? Now, that's this axis, x-axis, real part. The imaginary part corresponds to oscillation frequency. Okay? If that is 0 and you're on the real axis, there is no oscillation of any kind. In other words, the solutions look like e to the t, e to the minus t, 1. Okay? If you're complex, there is oscillation. Okay? And in fact, your height above the real axis, which is to say that your imaginary part of the pole determines the oscillation frequency. Okay? So for example, this pole corresponds to a rather rapidly growing and sinusoidally oscillating solution. Okay? What does this correspond to? If you had a pole there, and of course then by conjugate symmetry you have a pole here. What does that pole correspond to? Just qualitatively, what is it? It's a slowly decaying oscillatory term. Okay. And now just for fun, what about zeros? What if I tell you that here are the zeros? What does that tell you about the qualitative types of terms? What does it mean? Absolutely nothing whatsoever. That's what it means. Okay? It means something different, and we'll get to what it means. But it means absolutely nothing in terms of what the types of terms are. Okay? That means nothing. The poles.
The oscillation frequency is just the distance away from the real axis.
That's it. It's the height. That's omega right there. Yeah. Now, let me give you a couple of warnings, one of which, if you've done this week's homework, you're probably a little bit aware of already. It turns out that when you see a pole like that, that is a rapidly decaying oscillation with a low frequency. Now, this is kind of obvious, but let me just make a kind of a comment about this. So here you take something like a cosine or whatever, there it is, okay? Now, if this is decaying so fast that one time constant is sort of like this, right? In other words, if I multiply that by this, okay, I'm going to get a solution where your eyeball will not say that's an oscillatory solution. You know what I'm saying here? In other words, when you multiply these two together, you're going to get one bump. It's going to kind of look like this. It's going to kind of go, and that's it. It'll actually it'll be negative down here, sorry, like that, and then that's it. So your eye will be able to discern one bump, maybe one zero crossing, just barely. So I mention this because, well, it's related to your homework, I think. It's related to a problem on your homework. So the point is, be aware that a rapidly decaying sinusoid might not. I mean, everyone thinks about rapidly decaying sinusoids, and this is the picture everyone has in their mind, where it's clear it's rapidly decaying because you see the oscillation, and every cycle it gets 5% smaller. But remember that a single bump can be what is visually taken to be a single bump can actually be an exponentially decreasing sinusoid. Okay, so that's the idea. Now there's all sorts of ways to understand this. You have to be able to go back and forth between solutions and the time domain and the pole locations and so on. Now, for complex poles, there's a number of terms that people use to describe them, and one is this: if you have we'll look at the two that are very common are damping ratio and Q, and they're used in different fields. And in fact, I'll say a little bit about that in a few minutes because it's kind of interesting. So if you have a pole at sigma plus j omega, then of course you also have one at sigma bar, which is sigma lambda bar, which is sigma minus j omega. Then the term is going to be, you put these two together, and actually we don't really care about how they come out to affect the phase and the amplitude. We don't care about that. You can do that. You could have done it in 101. Doesn't matter. The important part is that the pole terms, the sigma and the omega, find themselves as the frequency and as the exponent in the growth or decay rate here. Let's assume that this is decaying, so sigma is negative. Then there's several measures of the decay rate per cycle of oscillation, and this is related to what I was just talking about, right? The question is, how much do you decay per cycle? And in fact, it's clear that what's involved in decay per cycle is actually really interesting. It's obviously an angle, and let's say why that is. If this is oscillation frequency and this is growth rate, then it's the angle that tells you how much you decay per oscillation frequency. It's a ratio of two frequencies, which makes perfect sense. So let's work out how that is. Here they are. Let's see. These two measures are the damping ratio, which is minus sigma over sigma squared plus omega squared, and the quality factor Q. These are given in different fields, and so they're all given geometrically by something related to this angle. I mean, one of them is something like this divided by that, and the other is something else. They're simply related. Okay, and what it basically says is when this angle is small. When you see a pole up here, it corresponds to, people would refer to that as a lightly damped pole. That would be universal description of this. That's universal. That would be, you would discuss this in talking about aircraft dynamics, the dynamics of a building that was built, and discussing its response to an earthquake. You would talk about this in a high-speed interface circuit or something like that. This is what you'd say. And what you'd do is someone you'd see on an oscilloscope or something like that, or a seismograph or something, or some display, something, you'd see a slowly decaying sinusoid, and you'd say, there's some. You say, I'm sensing lightly damped poles here. Or if you're actually in an aircraft, I don't know. I guess after throwing up or something, then you'd say, lightly damped poles. Let's go back and try it again. Okay, so that's what this means. And that corresponds to a small angle here, and that's small damping, or actually high Q. And Q stands for quality factor, and I'll describe that. I'll say why it is in a minute. Down here, it's basically sort of at about a 45, it's a rough rule of thumb. It's at a 45-degree angle here, where it's at a 45-degree angle here, where these would sort of be visually, so here's the way I would divide up this complex plane. If you take like a 20-degree angle up here, these would, by the eyeball, you would perceive these as decaying sinusoids. You'd see the oscillation and so on. Okay? In this region, you would know that we had complex poles because you would actually see quite well that there are multiple zero crossings, and so you'd know that. On the other hand, you'd say, well, it's reasonably damped or something like that. And whether that's good enough for your application depends on what's happening. Okay? Over here, even though you've got complex poles, the overall dynamics is still that of just kind of a bump. There's kind of like a bump there. Maybe you see one zero crossing, maybe not even. And so that's out here. Now out here, of course, once you're in exponential land, it's just some linear combination of some exponentials decaying at different rates and so on. So that's the idea. Now what's interesting about this is another way to understand this, and we'll talk about that I guess next time, but a very good way to understand this is that in the complex plane, there's several ways to describe complex numbers. One is in terms of real and imaginary part. So for you, from now on, when we're talking poles, real part means decay rate or growth rate, depending on whether it's positive or negative. Period. That's what it means. Okay? Imaginary part, that's height of a pole in the complex plane. That gives you oscillation frequency. Now another way to describe a complex number is very interesting, is by magnitude and phase. That's by magnitude is how far it is here, and then its angle. Now, what does angle determine of a pole in complex plane? Well, it determines growth rate or decay rate per cycle of oscillation. If the angle is 0, there's no oscillation, so it doesn't make any sense. Or if it's 180. But if it's up here, that's something which grows a little bit per cycle of oscillation. This is something that shrinks a little bit per cycle of oscillation. and so on. So the angle tells you the growth or decay rate per cycle of oscillation, and the magnitude gives you the time scale. That's what it is. Okay, gives you the time scale. So that's what magnitude and angle mean for a pole. So in other words, poles way down in here, so these are poles with small complex magnitude. They correspond to things in the time domain which happen slowly. Everyone got that? So in other words, I said, well, this thing has got a really small pole. What does the inverse Laplace transform look like? And you'd say, well, excuse me, but you have to tell me, like, if the real part is negative or positive, are they real or imaginary? And you say, no, I have no intention of telling you. All I'm telling you is the pole is small. Okay? Then there is actually an answer, and the answer is, I don't know what it is. It depends. If it's real and positive, it corresponds to, notice, slow growth. If it's real and negative, it corresponds to slow decay. If it's pure imaginary, it corresponds to slow oscillation. In summary, a small pole corresponds to slow in the time domain. Does that make sense? Well, of course, because what's the unit of a pole? The unit of a pole is frequency. It's 1/seconds. So if 1/seconds is really small, the inverse of a pole is time. Long time. Long time to double, long time to shrink, long time to go through a cycle. Okay? Conversely, a big pole, people often refer to as a fast pole. So a large pole is a fast pole. Okay, we'll quit here.